how many numbers would it take to describe the universe itself? Not any particular galaxy within it, not any particular star, not even the comparatively modest task of describing the swirling architecture of a galaxy cluster. The whole thing, all of it. From the first fraction of a second to the distant future when the last black holes have finally evaporated away. You might expect the answer to be something enormous. After all, the universe contains something in the region of 2 trillion galaxies, each of which contains hundreds of billions of stars. And each of those stars, with its planets and moons and asteroids and clouds of drifting gas, is already a near infinite catalog of detail. Surely, describing all of this would require a number so large it would take longer than the age of the universe just to write down. And yet, physicists believe that at the deepest level, the entire history and future of the universe may be encoded in a surprisingly compact set of numbers, a set small enough to fit on a single page. And not just any numbers, but specific dimensionless ratios, pure quantities with no units attached. Numbers that describe the fundamental relationships between the forces and particles that build everything we see. Change any one of them even slightly, and the stars would never have formed. The atoms in your body could not have assembled. The universe would exist, but nothing interesting would ever have happened in it. These are the constants of nature. And what we know and don't know about them is one of the strangest and most profound stories in all of physics. Let's begin with something familiar. A simple ratio you learned about in school. Take any circle anywhere in the universe, measure its circumference, measure its diameter, divide one by the other. You will always get the same answer: pi, 3.14159, and on into the digits forever. This is a mathematical constant. It emerges from the geometry of flat space and has nothing to do with experiment. No measurement could change it. No version of the universe could have a different value of pi. Physical constants are different. They are not determined by mathematics alone. They are determined by how the universe actually behaves. You can only find them by doing experiments. And the strange thing is that we have no theoretical reason to think they have the values they do. We cannot derive them from first principles. We cannot prove from pure logic that the electron must have the mass it has, or that gravity must be as weak as it is relative to the other forces. We measure these things and write them down and build our theories around the numbers the universe hands us. And then we ask why. The most fundamental of these constants sit at the heart of the standard model of particle physics and the general theory of relativity. Combined, these two frameworks give us the best description we have of physical reality at every scale, from the subatomic to the cosmological. And together, they require roughly 26 independent parameters, 26 numbers that have to be measured and fed into the theory. Without them, the equations have nothing to work with. They are the skeleton the universe is built on. To understand why these numbers matter so much, it helps to think about what they actually control. Some of them set the masses of particles. The up quark is about 2 mega-electron-volts in mass. The down quark around 5. The top quark, the heaviest of the 6 quarks, is roughly 173,000 mega-electron-volts. These are not round numbers. They are not particularly elegant. They look almost arbitrary. And the question of why the top quark is so much heavier than the up quark by a factor of around 85,000 has no answer in current physics. It simply is. Other constants set the strengths of the fundamental forces. The strong nuclear force is characterized by its coupling constant, the weak force by its own, electromagnetism by the fine structure constant, gravity by Newton's gravitational constant. Each of these numbers sets how strongly the corresponding force acts when particles interact, and they are wildly different from each other in a way that turns out to be extremely important. The fine structure constant alpha is perhaps the most famous of these. It is a pure dimensionless number, approximately equal to 1/137. No units, just a number. It sets the strength of the electromagnetic interaction between charged particles. When an electron and a proton attract each other electromagnetically, the fine structure constant is what determines how hard they pull. Richard Feynman, who spent considerable time thinking about this number, wrote that it has been a mystery ever since it was discovered more than 50 years ago, and all good theoretical physicists put this number up on their wall and worry about it. It is one of the greatest damn mysteries of physics. The mystery is this: nobody knows why it is 1/137. It is not 1/100. It is not 1/200. It is not derived from any deeper principle. If you asked a theoretical physicist to predict the fine structure constant from first principles before anyone had measured it, they could not do it. You simply go and measure it, and get 1/137, and then you build your theory around that number. The number comes from outside the theory. It is an input, not an output. To feel the weight of this mystery properly, it helps to think about what would happen if these constants had different values. Not wildly different values, necessarily, just slightly different. The sensitivity of the universe to small changes in its fundamental constants is genuinely extraordinary. Consider the strong force coupling constant. This is the number that sets how powerfully quarks bind together to form protons and neutrons, and how tightly protons and neutrons then bind together inside atomic nuclei. The value of this coupling determines, among other things, the precise energies of nuclear reactions inside stars, and it turns out that carbon and oxygen, the two elements most essential to life as we know it, are both products of stellar nucleosynthesis, the process by which stars forge heavier elements from lighter ones. Carbon is produced when 3 helium nuclei collide and fuse in a sequence of reactions inside massive stars. This works with the current value of the strong force coupling constant, because there happens to be a resonance in the carbon-12 nucleus, an excited energy state at almost exactly the right energy to make the triple alpha process, as physicists call it, enormously more efficient than it would otherwise be. This resonance was actually predicted before it was measured. The physicist Fred Hoyle reasoned that carbon must have such a resonance, otherwise there would be no carbon in the universe, and therefore no life, and therefore no Fred Hoyle reasoning about carbon. His prediction was confirmed experimentally. The resonance is there, but the existence of this resonance depends critically on the value of the strong force, coupling constant, and the value of the electromagnetic fine structure constant. Shift either of them by more than a few percent, and the resonance moves out of the right energy range. Carbon synthesis becomes vastly less efficient. The universe ends up with far less carbon than ours has. And it is not just carbon. If the strong force were slightly stronger, protons and neutrons would bind together so tightly that hydrogen would never exist in free form. the whole universe would fuse into helium in the first few minutes. There would be no stars burning hydrogen for billions of years, providing the stable energy source that life requires. If it were slightly weaker, the opposite problem. Nuclei beyond hydrogen would barely bind at all. The periodic table would be almost empty. Chemistry, as we know it, would not exist. The example of carbon is just one of dozens of similar coincidences and near misses that physicists have catalogued over the decades. The ratio of the electromagnetic force to gravity is 10 to the power of 36. Gravity is extraordinarily weaker than electromagnetism. This enormous ratio is actually necessary for stars to exist at all. Stars work by balancing the inward pull of gravity with the outward pressure of radiation and thermal energy produced by nuclear fusion. The stronger gravity is relative to the other forces, the faster things fall together, the shorter the stellar lifetime. If gravity were even a tiny fraction of the strength of electromagnetism, stars would burn out in seconds. Planets would have no time to form. Life would certainly have no time to evolve. The weakness of gravity relative to the other forces is not just a curiosity. It is what gives the universe its vast timescales, its billions of years of stellar evolution, its patient geological processes on planets that cook simple chemistry into complex molecules. Without the enormous ratio between gravity and electromagnetism, none of this happens. And we have no explanation for why that ratio has the value it does. The cosmological constant is perhaps the most dramatic example of fine-tuning in physics. When Einstein first wrote down his equations of general relativity, he included a term he called the cosmological constant, a number representing an intrinsic energy density of empty space. He later abandoned it when it became clear the universe was expanding, rather than static. But quantum field theory, the theoretical framework underlying the standard model of particle physics, predicts that empty space should have an energy density arising from quantum fluctuations of all the fields that exist in nature. When physicists calculate this predicted vacuum energy, they get a number roughly 10 to the power of 120 times larger than the value of the cosmological constant actually observed from the way the universe's expansion accelerates. 10 to the power of 120 is not a small discrepancy. It is the largest discrepancy between theory and observation in the history of science. Something is canceling the enormous predicted vacuum energy down to the tiny observed value with a precision of 120 decimal places. What is doing the canceling? Nobody knows. This is called the cosmological constant problem, and it is arguably the deepest unsolved problem in theoretical physics. The fact that the cosmological constant is as small as it is, rather than taking the value quantum field theory naively predicts, is essential for the existence of the universe as we know it. A cosmological constant of the predicted size would cause the universe to expand so rapidly that no structure of any kind galaxies, stars, planets, atoms could ever form. The story of how physicists came to take these questions seriously has its own history. For much of the 20th century, discussing the fine-tuning of physical constants was considered vaguely disreputable. It smelled of teleology, of arguments from design. If you noted that the constants seemed adjusted to permit life, it sounded like you were smuggling religion into physics through the back door. Serious physicists focused on the equations and left questions about why those equations had their particular parameters to philosophers. This changed gradually as the magnitude of the fine-tuning became clearer. By the 1970s, the astrophysicist Brandon Carter had developed what he called the anthropic principle in a careful and specific form. His point was not mystical, it was statistical. Any universe whose constants do not permit the existence of observers will never be observed. This is a selection effect, not a design argument. We find ourselves in a universe that permits our existence for the trivially simple reason that if it did not, we would not be here to find anything. The question of whether constants finely tuned for life should surprise us depends entirely on what set of possibilities we are sampling from. If there is only one universe with only one set of constants, then the fine-tuning is deeply mysterious. Either the constants were chosen for some reason, or they happen to take life-permitting values by extraordinary luck. But if there are many universes each with a different set of constants, drawn from some distribution, then the fine-tuning becomes comprehensible. We necessarily find ourselves in one of the rare universes where the constants permit our existence. The others exist, but are unobserved because they contain no observers. This brings us to one of the most contested and fascinating ideas in modern cosmology, the multiverse. Not in the science fiction sense of parallel worlds branching off at every quantum event, though that is also a legitimate interpretation of quantum mechanics, but in a specific cosmological sense arising from the theory of cosmic inflation. Inflation is the proposal first developed by the physicist Alan Guth in 1980, that the very early universe underwent a period of exponentially rapid expansion, driven by the energy of a field called the inflaton. In a tiny fraction of a second, the universe expanded by a factor of at least 10 to the power of 26, possibly enormously more. Inflation was proposed to solve specific observational puzzles. Why is the cosmic microwave background so uniform in temperature in all directions, even in regions that could never have been in causal contact? Why is the spatial geometry of the universe so close to perfectly flat? Inflation solves both of these by stretching any initial inhomogeneities and curvature to scales far larger than the observable universe, making our visible patch appear smooth and flat, regardless of what initial conditions it started from. Inflation is now supported by considerable observational evidence. The spectrum of tiny temperature fluctuations in the cosmic microwave background matches the predictions of inflationary models with impressive precision. The fluctuations are slightly stronger at large scales than small ones in a characteristic way that inflation naturally produces. And the overall flatness of the universe is exactly what inflation predicts. But inflation has a theoretical feature that was initially awkward and has become increasingly central to how physicists think about fine-tuning. In most models of inflation, once inflation starts, it does not stop globally. It stops locally in some region, creating a bubble of slower expansion that eventually becomes a universe like ours. But in the wider inflating background, inflation continues producing more and more such bubbles indefinitely. This process, called eternal inflation, generates an effectively infinite collection of pocket universes, each potentially with different values of the fundamental constants, depending on how the inflaton field settles into its ground state in each bubble. String theory, which proposes that the fundamental objects in nature are not point-like particles, but tiny, one-dimensional vibrating strings, provides a possible mechanism for this variation. String theory requires extra spatial dimensions beyond the three we experience, and these extra dimensions can be curled up in an enormous variety of ways, each corresponding to a different effective low-energy physics, with different values of the coupling constants and particle masses. The number of distinct ways to compactify the extra dimensions is estimated to be something like 10 to the power of 500. Each compactification corresponds to a different set of physical laws. The string theory landscape, as it has come to be called, potentially provides an enormous ensemble of possible universes, each with its own constants. In the landscape, picture the fine tuning of the constants is explained statistically. With 10 to the power of 500 possible sets of constants, most of the possibilities are hostile to life. But the fraction of constants that permit life, while tiny in proportion, still corresponds to an enormous absolute number of life-permitting universes. And we necessarily find ourselves in one of them. The cosmological constant, which requires the most spectacular fine-tuning of any known constant, turns out in the landscape picture to have a natural explanation. Almost all values of the cosmological constant, either positive or negative, are far too large for structure to form. Only values in a narrow window around zero permit galaxies, stars, and planets to exist. Before the 1998 discovery that the universe's expansion is accelerating, the theoretical physicist Steven Weinberg predicted, on this basis, that if the landscape existed, the cosmological constant should be non-zero, but small enough to permit galaxy formation. His estimate was within an order of magnitude of the subsequently measured value. That is a striking piece of evidence, though not proof. Not everyone finds the landscape picture satisfying. The physicist Lee Smolin has argued that it is not genuinely predictive, because with enough vacua, almost any observation can be accommodated after the fact. Others point out that the anthropic selection argument requires careful specification of what counts as an observer and what probability measure to use when sampling from the landscape, both of which are genuinely difficult problems. The measure problem of inflation, as it is called, is unsolved. Without knowing the probability distribution over the landscape, we cannot make precise predictions from it. But let's step back from the multiverse for a moment and ask a simpler question. Could the constants be different from a theoretical standpoint? Is there any reason internal to physics why they should take the values they do? This is the hope that drove much of 20th century fundamental physics. The search for a final theory, a framework from which all the constants of nature could in principle be derived. Einstein spent the last 30 years of his life searching for a unified field theory that would derive electromagnetism and gravity from a single geometric principle, and along the way, fix all the parameters. He did not succeed. The Standard Model unifies electromagnetism with the weak nuclear force into a single electroweak framework, and this unification fixes some relationships between previously independent parameters. But the Standard Model still requires around 26 measured inputs. It does not derive them. Grand, unified theories that attempt to extend the unification to include the strong force, as well, predict that the strong electromagnetic and weak coupling constants should all converge to the same value at very high energies. This prediction has been tested. In the simplest grand unified theory, the convergence is not quite exact when you run the coupling constants up to high energies using the renormalization group equations. But in the minimal supersymmetric extension of the Standard Model, which pairs every known particle with a heavier superpartner, the three couplings do converge to a single point at around 10 to the power of 16 gigaelectronvolts. This is sometimes cited as indirect evidence for both grand unification and supersymmetry. The Large Hadron Collider searched for the superpartner particles predicted by supersymmetry and has so far not found them at the masses that were most hoped for. The search continues at higher energies. String theory is the most ambitious attempt to derive everything from a single underlying framework. If string theory is correct, then in principle, the values of all the constants should be derivable from the geometry of the extra dimensions. But, as we have noted, the landscape of possible compactifications is enormous. The theory does not point to a unique vacuum. It does not single out our particular set of constants. It predicts many possible sets, and ours is one of them. Whether string theory will eventually provide a mechanism for selecting our vacuum uniquely, or whether the selection is purely anthropic, is one of the deepest open questions in fundamental physics. There is another angle on the constants that deserves serious attention: the question of whether they actually are constant, whether the fundamental numbers of physics have been the same throughout cosmic history, or whether they change over time or vary from place to place, is a question that can, in principle, be answered observationally. The fine structure constant is particularly useful for this purpose because it governs the wavelengths of spectral lines, the specific frequencies of light absorbed and emitted by atoms. These wavelengths depend on the fine structure constant in a calculable way, and we can observe spectral lines from extremely distant quasars' light that has been traveling for billions of years before reaching us, and compare them to the same spectral lines measured in laboratories on Earth today. If the fine structure constant has changed over the history of the universe, the quasar spectral lines would be shifted by a different amount than a simple cosmological redshift predicts. In 2001, a team led by John Webb at the University of New South Wales analyzed observations of quasar spectra made with the Keck telescope in Hawaii and reported evidence for a very small variation in alpha over cosmological timescales. The variation claimed was tiny at the level of a few parts per million, but it was statistically significant in their data, and it pointed in the direction of a smaller alpha in the distant past. This was an extraordinary claim, if true. A varying fine structure constant would violate one of the foundational assumptions of physics, the principle of local position invariance, which holds that the laws of physics are the same everywhere and at all times. Subsequent observations with the Very Large Telescope in Chile and later with other instruments gave partially contradictory results, some supporting a variation and some not. The question of whether alpha varies with cosmic time or position in space remains genuinely open. More recently, Webb and colleagues have suggested that the data show a spatial variation as well, that alpha may be slightly larger in one direction of the sky and slightly smaller in the opposite direction, like a cosmic dipole. This result has generated considerable interest and ongoing scrutiny. The possibility of spatially varying constants connects to a broader question about the nature of the constants themselves. In standard physics, the constants are treated as numbers that are fed into the theory from outside. They are parameters, not predictions. They do not have dynamics. They do not respond to their environment. They just sit there characterizing the theory. But in some extensions of standard physics, constants can become dynamical. In Brand's-Dicke theory, a modification of general relativity proposed in 1961, the gravitational constant g is promoted to a scalar field that varies across spacetime. The theory reduces to general relativity in a certain limit and passes the same observational tests that general relativity passes in that limit, but in principle predicts that gravity was slightly stronger in the early universe than it is today. Observational constraints from the solar system, from the orbit of Mercury, from the measurement of gravitational wave propagation, and from cosmological data now place very tight limits on how much g can vary. But the limits are not zero. Some variation is still permitted within current measurement precision. More speculatively, the moduli fields in string theory are scalar fields associated with the sizes and shapes of the extra dimensions. If these fields have not yet settled into their ground state, they would still be slowly rolling through their potential. And as they roll, the effective four-dimensional coupling constants and masses that we measure would slowly change. The universe would be aging in a way we have not yet detected, not just cooling and expanding, but slowly drifting in the values of its fundamental constants. What would it mean if we discovered that the constants were changing? It would mean that what we thought were fixed features of reality are actually dynamical, evolving quantities. That the laws of physics, as we currently write them, are approximations valid over the range of cosmic history we have sampled, but not eternal. That the universe has a deeper physics underlying the Standard Model and general relativity, within which our apparently constant constants are slowly varying fields. It would also raise an extraordinary question. If the constants are fields that can vary, does that mean we could in principle change them deliberately? Could a sufficiently advanced civilization adjust the local value of the fine structure constant, or the strong force coupling constant, and in doing so alter the local laws of physics? This is speculation so far beyond current technology as to be almost meaningless. But it is the kind of speculation that physics licenses in a way that other subjects do not, because the constants have already been shown to be at least potentially dynamical. The step from dynamical to controllable is enormous, but it is not obviously infinite. Let's come back to the deepest version of the question. Why these numbers? Of all the possible values the constants could take, why do we find ourselves with the specific values that exist in our universe? There are essentially three possible answers that physicists take seriously. The first is necessity. Perhaps there is a final theory from which all the constants can be derived uniquely. Perhaps once you write down the correct equations, they have a unique solution that fixes every parameter, and that solution happens to be the one our universe corresponds to. This was Einstein's hope. It remains the hope of many theoretical physicists. String theory was once thought to be this final theory, uniquely determined by internal mathematical consistency. It turned out to have an enormous landscape of solutions, rather than a unique one. But the hope of necessity has not been entirely abandoned. There may be principles we have not yet discovered that select uniquely among the possible string vacua, or among possible theories more broadly. The second answer is chance. The constants take the values they do by accident. We happen to live in a universe where they have these values, and there is no deeper explanation. This is unsatisfying to most physicists because it seems to explain nothing, but it is logically coherent. We have no proof that the universe requires an explanation. It could simply be the way it is. The third answer is selection. The constants take the values they do in our observable universe, because only universes with approximately these values contain observers. In a multiverse, the constants take many values. We observe the values we do because we are here to observe them. This is the anthropic argument, and as we have discussed, it comes in many forms, from the weak anthropic principle, which merely notes the selection effect, to specific quantitative predictions, like Weinberg's prediction of the cosmological constant that can be tested against observation. Of these three possibilities, selection has recently received the most attention, partly because it seems to require the fewest additional assumptions. Eternal inflation appears to follow from generic inflationary models, and eternal inflation generates a multiverse. String theory predicts a landscape. The combination of the two provides a specific mechanism for generating an ensemble of universes with varying constants, and the anthropic selection within this ensemble provides an explanation, at least in principle, for fine-tuning. This does not mean the argument is correct. The measure problem is severe. The framework is not currently falsifiable in the way that scientific theories ideally are, but it is a coherent program, and it has produced at least one successful prediction in the form of the cosmological constant. There is a different tradition in the study of physical constants that deserves mention before we go further. A tradition less concerned with why the constants have their values, and more concerned with whether there are fewer independent constants than there appear to be, whether some apparent constants can be derived from others. The mass of the electron, for example, is one of the input parameters of the Standard Model. You feed it in by hand based on measurement, and the theory uses it to make predictions. But the electron also interacts with the Higgs field, and the strength of that interaction determines the electron mass. In the electroweak theory, the electron mass can be written as the product of the Higgs field vacuum expectation value and a dimensionless coupling constant called the Yukawa coupling. So you can replace one parameter, the electron mass, with another, the Yukawa coupling. The number of independent parameters has not really decreased. You have just rewritten one in terms of others. True reduction in the number of independent parameters happens when unification occurs. The electroweak theory unifies electromagnetism and the weak force, and in doing so, replaces two independent coupling constants with 1 + a mixing angle. That is a genuine reduction, though a modest one. Grand unification, if successful, would replace the three independent coupling constants of the strong electroweak and electromagnetic forces with one coupling at high energies and a set of symmetry-breaking parameters at low energies. String theory ultimately aims to derive everything from a single underlying framework with no free parameters at all. The geometry of the extra dimensions would determine all the coupling constants and particle masses uniquely. Whether this ambition will ever be realized is unknown, but even attempting it requires first knowing precisely what the constants are and how they relate to each other. And this requires the most precise possible measurements. The precision with which the fundamental constants are known varies enormously. Some are measured with extraordinary accuracy. The fine structure constant is now known to about 12 significant figures, thanks to measurements of the anomalous magnetic moment of the electron combined with precise QED calculations. The electron-to-proton mass ratio is known to 11 significant figures. These are among the most precisely measured quantities in all of science. Others are known far less precisely. The gravitational constant g is among the least precisely measured of the fundamental constants, despite being the oldest known. Newton himself effectively determined g up to a normalization through his laws of motion and gravitation. Henry Cavendish in 1798 made the first laboratory measurement of g using a torsion balance to measure the tiny gravitational attraction between lead spheres. 2 centuries of refinement later, G is still only known to about 5 significant figures. This is not a failure of experimental technique. It reflects the extraordinary weakness of gravity relative to other forces. The gravitational attraction between 2 lead spheres in a laboratory is dwarfed by electromagnetic noise and thermal fluctuations, and even by the gravitational effects of traffic on nearby roads. Getting a clean measurement requires extraordinary isolation and patience. There is one constant whose status has been deeply controversial in recent years: the Hubble constant H0, which measures the current rate of expansion of the universe. Unlike the particle physics constants, which are properties of spacetime itself, the Hubble constant is in principle a time-varying quantity, since the expansion rate changes as the universe evolves. But its current value is a fundamental parameter of the standard cosmological model. 2 different methods of measuring H0 give different answers. Observations of the cosmic microwave background combined with the standard cosmological model give a value around 67.4 kilometers per second per megaparsec. Direct measurements of the local universe using the cosmic distance ladder built from Cepheid variable stars and Type 1a supernovas give a value around 73 kilometers per second per megaparsec. This discrepancy, called the Hubble tension, is now statistically significant at around 5 sigma. One of these measurements is wrong, or the standard cosmological model is missing something important at some point in cosmic history. What might be missing? Early dark energy, a component of the universe's energy budget that was significant in the early universe before fading away, could shift the prediction from the CMB in the right direction. An additional species of neutrinos beyond the 3 we know about could similarly affect the early universe's expansion rate. Modified gravity could change the relationship between the CMB observations and the inferred expansion rate. None of these proposals has been confirmed. The Hubble tension may be the first sign of new physics beyond the standard cosmological model, or it may be an undetected systematic error in one of the measurements. Resolving it is one of the highest priorities in observational cosmology. The study of fundamental constants has an unexpected connection to the deepest questions about what makes physics possible in the first place. When we write down the equations of the standard model, we specify not just the values of the constants, but a particular mathematical structure. We assume that nature is described by quantum field theory. We assume specific symmetries. We choose specific particle content. These choices could in principle have been different. Why these symmetries? Why these particles? Why quantum field theory at all, rather than some other mathematical framework? These are questions that physics, as currently practiced, largely cannot address. We write down the equations because they describe what we observe. We do not derive them from anything more fundamental. This is not a failure of physicists, but a genuine epistemological limit. We describe, we predict, we test, but we do not ultimately explain why the framework for description is what it is. There are hints at a deeper story. The mathematician Eugene Wigner wrote in 1960 about what he called the unreasonable effectiveness of mathematics. Physical reality is described by mathematical structures with extraordinary precision. The equations of quantum electrodynamics predict the magnetic moment of the electron to 12 decimal places. General relativity predicts the rate of energy loss from binary pulsar systems to better than 1 part in a trillion. This agreement is not trivial. It is not forced by the act of writing down equations. Plenty of mathematical structures describe nothing physical at all. The fact that specific, simple mathematical frameworks describe physical reality with this precision is itself something that requires explanation. One possibility is that mathematical structures do not merely describe physical reality, but are physical reality. The physicist Max Tegmark has argued that every mathematical structure that is self-consistent and well-defined has a physical existence, and we find ourselves in one of them. This is the mathematical universe hypothesis. Like the multiverse of eternal inflation, it is a framework that potentially explains fine-tuning through selection. We find ourselves in a mathematical structure that permits our existence, but it is even broader than the physical multiverse. It encompasses every possible mathematics. These ideas are at the far frontier of what can currently be called physics. They make no predictions that can be tested with any foreseeable technology. They are frameworks for thinking, not completed theories. But they are taken seriously by serious physicists because the questions they address the questions of why these constants, why these laws, why these mathematical structures are genuine questions, and they deserve genuine attempts at answers. What we know is this: the universe runs on 26 or so numbers that we have measured and cannot currently explain. Change them, and the universe becomes lifeless. Some of them may vary across space and time. Some of them may eventually be derivable from a deeper theory. Some of them may be selected anthropically from a larger ensemble. We do not know which of these is the right story. We may not know for a long time. What we can do is keep measuring. Increasingly precise measurements of the fine structure, constant of the electron mass of the proton radius, of the gravitational constant, will constrain what theories are possible. Observations of quasar spectra across cosmic time will test whether alpha varies. Gravitational wave observations from merging neutron stars and black holes will test whether G has evolved since the early universe. The Euclid telescope and the Vera Rubin Observatory will constrain the dark energy equation of state with unprecedented precision, potentially distinguishing a true cosmological constant from a dynamical field. And at particle accelerators pushing to ever higher energies, experimenters will search for the superpartner particles that supersymmetry predicts, for the signs of grand unification, for hints of extra dimensions, and for whatever lies beyond the standard model. Each discovery or non-discovery will constrain the theoretical landscape and push the understanding of the constants further. There is something philosophically remarkable about the situation we find ourselves in. We are creatures whose existence depends on specific values of numbers we cannot explain. The carbon in our bones required a resonance in the carbon-12 nucleus that required specific values of the strong force coupling constant. The hydrogen that makes up most of the atoms in our bodies required a universe that did not fuse all its hydrogen into helium in the first minutes, which required specific values of the gravitational constant and the weak force coupling. The long, stable, stellar lifetimes that powered the evolution of life on Earth required gravity to be as weak as it is relative to electromagnetism. We are made of fine tuning. The constants that seem so arbitrary, the numbers that float free of any theoretical explanation, they are not merely abstract features of a theory. They are the reason we exist. Change any one of them beyond narrow limits, and we are not here to be surprised by anything. This could be coincidence. It could be necessity. It could be selection from an enormous ensemble. Any of these possibilities is more strange and more interesting than the naive assumption that physics just happens to describe a universe, and the universe just happens to contain us. The constants of nature sit at the intersection of fundamental physics cosmology and the deepest questions about existence and why anything is the way it is at all. The answers are not yet in. The measurements continue. The theories are written and rewritten. And on laboratory walls around the world, the fine structure constant 1/137 continues to stare back at physicists who have not yet stopped wondering why. What we do not know about these 26 numbers may matter more than what we do, because somewhere in the gap between the measured values and the theoretical explanation lies either the discovery that the universe is ultimately comprehensible in a final theory that fixes everything, or the discovery that we live in one of an enormous number of possible universes, each with its own constants, and ours simply happens to be the one that permitted us to ask the question. Either answer would be among the most profound discoveries in the history of human thought, and both remain genuinely open. The universe is still keeping its deepest numbers to itself, but it has never yet succeeded in keeping a secret forever. But before we get there, let's go back to the beginning of how physicists began to appreciate that these numbers were special. Because for a long time, the constants were simply part of the scenery. You measured them. You wrote them in tables. You used them in calculations. The idea that they might have been different or that their specific values carried a kind of information about the nature of reality was slow to develop. The person who did more than anyone else to bring this question into focus was the Cambridge theoretical physicist Paul Dirac. In 1937, Dirac noticed something striking when he started comparing the fundamental constants of physics in different combinations. The ratio of the electromagnetic force to the gravitational force between a proton and an electron is approximately 10 to the power of 39. The ratio of the age of the universe to the time it takes light to cross a proton is also approximately 10 to the power of 39. These two numbers from completely different domains of physics, particle physics on the one hand and cosmology on the other, were approximately equal. Dirac thought this could not be a coincidence. His large number hypothesis proposed that these ratios were equal for a reason and would remain equal as the universe evolved. But the age of the universe changes over time. If the ratio involving cosmological time is always equal to the ratio involving fundamental constants, then either the fundamental constants are also changing with time, or the hypothesis is wrong. Dirac concluded that the gravitational constant g must be decreasing over cosmic time. The universe was getting older, and g was getting correspondingly weaker. This was a striking prediction, and it has been tested. If g were decreasing, then the sun would have been brighter in the past, since stellar luminosity depends on g and on nuclear reaction rates. Geological evidence from the ancient Earth and from the Moon suggest that the sun was not dramatically different in its early history from what it is today. Pulsar timing gives very precise constraints on whether g is changing. Measurements of the orbits of the outer planets constrain the rate of change of g very tightly. The consensus of these measurements is that if g is changing at all, it is changing far more slowly than Dirac's hypothesis requires. The large number coincidence may be a coincidence after all, or it may reflect a selection effect, rather than a dynamical equality. But Dirac's insight that the numbers themselves deserved attention, and that their relationships might carry information, was prescient. He shifted the conversation from how do we use the constants to why do the constants have these values, and whether they are truly constant at all. He opened a door that has not been closed since. The question of what counts as a meaningful physical constant is itself subtle and important. A physical constant is only physically meaningful if it is dimensionless. That is, if it has no units attached. Constants with units like the speed of light c, or Planck's constant h, or the gravitational constant g, depend on what system of units you choose to measure them in. You can make them equal to 1 by choosing the right units. Physicists routinely do exactly this using natural units, where c equals 1 and h bar equals 1. Only dimensionless combinations of constants carry genuine physical content independent of how you choose to measure things. The fine structure constant alpha is the archetypal example. It equals approximately 1/137th, regardless of whether you measure things in SI units or CG S units or natural units or any other units at all. It is a pure number, a ratio that describes something intrinsic about how electromagnetism works. Similarly, the proton-to-electron mass ratio, roughly 1,836, is dimensionless and physically meaningful. So is the ratio of the cosmological constant to the Planck energy density. These pure numbers are what a physicist from a completely alien civilization using completely different units would write on their wall as the meaningful parameters of the universe. This point matters for the multiverse discussion because it clarifies what is actually varying between hypothetical universes. It is not the speed of light in meters per second that varies, because that depends on arbitrary unit choices. It is the dimensionless combinations like alpha that vary. A universe with a different value of alpha genuinely has different physics in a way that cannot be made equivalent to our universe by a redefinition of units. The electron and proton couple to the electromagnetic field differently. Atomic structure is different. Chemistry is different. Everything is different. One of the most productive recent approaches to understanding the constants has come from the mathematics of the renormalization group developed in the 1960s and 1970s. This framework describes how the apparent strength of physical forces and the apparent masses of particles depend on the energy scale at which you probe them. The coupling constants of the Standard Model are not truly constant. They run with energy. The fine structure constant alpha is approximately 1/137. At low energies, the energies relevant to the hydrogen atom or to ordinary atomic physics. But at the energy of the Z boson around 91 giga-electron-volts alpha is approximately 1/128. The electromagnetic coupling has run to a larger value at higher energies. The strong coupling constant does the opposite. It is large at low energies, explaining why quarks are permanently confined inside protons and neutrons, and it decreases at high energies, explaining why quarks inside a proton at high momentum transfer behave almost as free particles. This property, called asymptotic freedom, won its discoverers Gross-Politzer and Wilczek the 2004 Nobel Prize in Physics. The running of coupling constants is one of the most direct pieces of evidence that there is more physics beyond the Standard Model at higher energies. When you extrapolate the running of the three coupling constants to very high energies, they do not quite meet at a single point in the Standard Model. But in the minimal supersymmetric Standard Model, they converge with striking precision. The coupling constants themselves contain information about the structure of the theory and about what physics might lie above the current experimental frontier. The precision measurement of constants has itself become a frontier of physics. Atomic clocks are now so precise that they can measure the gravitational redshift between a clock on the floor and a clock on a table, a height difference of 30 centimeters. The gravitational potential difference between these two positions causes a tiny but measurable difference in the rate at which time flows. This is not a thought experiment or a theoretical prediction. It has been measured directly with modern optical atomic clocks built around strontium or ytterbium atoms. The same atomic clocks can, in principle, detect whether the fine structure constant is drifting over time. The transition frequencies of atoms depend on alpha in a calculable way, and different atoms depend on alpha in different ways. By comparing two clocks based on different atomic species over a period of years, you can measure whether alpha is changing at a rate far below what astronomical observations can constrain. Current laboratory limits place the drift rate of alpha below about 10 to the power of minus 17 per year. This is a bound on the variation of a fundamental constant, more precise than almost any other measurement in physics. Future atomic clocks based on nuclear transitions, rather than electronic transitions, promise even greater sensitivity. The thorium-229 nuclear transition in particular is being actively developed as a nuclear clock. It sits at an energy so low for a nuclear transition that it can be driven by ultraviolet light, and its frequency depends on the strong force coupling constant in a way that makes it sensitive to drifts in that constant at extraordinary precision. If the strong force coupling is changing by even the tiniest fraction over geological timescales, these clocks may detect it. There is a tradition in physics of using the constants of nature to define natural units. Max Planck, in 1899, noticed that you could combine the gravitational constant g, the speed of light c, and Planck's constant h to form quantities with dimensions of length, time, and mass. The Planck length is approximately 10 to the power of minus 35 meters. The Planck time approximately 10 to the power of minus 43 seconds. The Planck mass approximately 10 to the power of minus 8 kilograms. These are the scales at which quantum gravitational effects are expected to become important, where the wavelength of a particle equals its own Schwarzschild radius. They are the scales at which our two best theories, quantum mechanics and general relativity, both apply simultaneously and where a theory combining them is required. The fact that the Planck length is so extraordinarily small compared to anything we can probe in the laboratory is another way of expressing the weakness of gravity relative to other forces. The Planck energy is about 10 to the power of 19 gigaelectron volts. The Large Hadron Collider reaches energies of about 10 to the power of 4 gigaelectron volts. The gap between the highest energy we can probe and the Planck scale spans 15 orders of magnitude. We have absolutely no experimental information about physics in that range. Whether it is genuinely empty or full of undiscovered phenomena, we cannot currently say. The hierarchy problem is the question of why the electroweak scale, where the Higgs mechanism operates, is so much smaller than the Planck scale. In natural units, the Higgs mass squared receives quantum corrections from virtual particles, and these corrections are proportional to the square of whatever mass scale represents the next layer of physics. If the next layer is the Planck scale, then the Higgs mass gets enormous corrections that have to be cancelled with extraordinary precision to give the observed Higgs mass of 125 gigaelectron volts. Either something physical cancels the corrections near the electroweak scale, or there is an extraordinary coincidence. Supersymmetry was the leading proposed solution, because superpartner particles contribute corrections opposite in sign to those of ordinary particles, and the cancellation is automatic. The non-observation of superpartners at the LHC has made the hierarchy problem more acute. It has not dissolved. Some physicists have argued that the constants point not to a multiverse, but to a specific structure in the space of possible theories. The dimensionality problem is one version of this. The laws of physics, as we know them, work in 3 spatial dimensions, plus 1 time dimension. Electrostatics and gravity both fall off with the square of distance because of the 3-dimensional geometry of space. In higher spatial dimensions, the force laws would be steeper. In lower spatial dimensions, weaker. The stability of planetary orbits depends on the force falling off as the inverse square. In 4 or more spatial dimensions, there are no stable orbits. Planets would spiral inward or outward rather than maintaining elliptical paths. Life, as we know it, could not exist in a universe with more than 3 spatial dimensions. Similarly, the 1-time dimension is special because it permits a consistent notion of causality. Multiple time dimensions allow closed, time-like curves, circular paths through spacetime that violate causality in ways that make the consistent evolution of physical systems impossible. This is a form of anthropic selection that works not through variation of constants, but through variation of the dimensionality of spacetime. It suggests that the constraint our existence places on the universe extends not just to the values of the constants, but to the topology and dimensionality of the space in which physics operates. Suppose we had a final theory. Suppose string theory or its successor produced a unique vacuum with every constant derived and every mass fixed. What would that mean? It would mean that the universe could not have been otherwise, not in any physically meaningful sense. The equations of the final theory would have a unique solution, and that solution would be our universe. The fine structure constant would be 1 over 137, because mathematics required it to be. There would be no fine tuning problem because there would be no free parameters to tune. The universe would be a theorem, not a coincidence. This is an extraordinary vision. It is the vision that motivated Einstein's 30-year search for a unified theory. It motivated Hermann Weyl, who wrote that the mathematics behind nature must be simple, beautiful, and complete. It motivated Dirac, who believed that the fundamental equations of physics must have great mathematical beauty. And it motivates theorists working on string theory today, even as the landscape threatens to undermine it. But there is a deep tension here. If the final theory has a unique solution, it presumably predicts not just the coupling constants, but also the initial conditions of the universe. It would predict why the universe started in a low entropy state, why it was homogeneous and isotropic on large scales, whether the Big Bang was truly a beginning or a transition from an earlier phase. A truly final theory would have to explain not just the laws, but the initial data. This is a boundary that current physics has not crossed. The Standard Model and general relativity together describe the evolution of the universe from very early times to the present with extraordinary accuracy. But they take initial conditions as given. They do not derive them. As we come back to the present moment, what is clear is that the constants of nature are not background furniture. They are not merely technical parameters to be plugged into equations and forgotten. They are the fundamental description of what the universe is and how it operates at the deepest level we have access to. Each one of them encodes an aspect of reality that could in principle have been different. The fact that they take the values they do, and that those values are precisely calibrated for the existence of stars and planets and chemistry and life, is either the most extraordinary coincidence in all of science, or it is pointing at something deep, either a final theory that derives them uniquely, or a multiverse from which we select them anthropically, or something else entirely that we have not yet conceived. The experiments continue. The atomic clocks tick. The telescopes collect light from distant quasars. The particle accelerators push to higher and higher energies. The theorists fill blackboards with equations in search of the deeper structure. Somewhere in this vast collective effort of measurement and calculation and imagination, the answer to why these 26 numbers, and not others, may eventually emerge. Many of the atoms that make up your body carry the imprint of the specific constants we have been discussing. The carbon-12 resonance that made stellar nucleosynthesis efficient enough to fill the universe with carbon required a precise relationship between the strong force, coupling constant, and the electromagnetic coupling. The fact that hydrogen exists at all required the strong force to be weak enough not to fuse it all into helium in the first 3 minutes. The fact that protons are stable on timescales of at least 10 to the power of 34 years required the proton-to-electron mass ratio to sit in a range where the decay channels are forbidden. You are not just a product of physics. You are a product of very specific physics. And that is why the question of why the constants have their values is not an abstract puzzle for theorists. It is a question about why you are here at all. The history of precision measurement is also the history of our slowly improving grip on these numbers. James Clerk Maxwell in the 1870s unified electricity and magnetism into a single framework, and in doing so, showed that the speed of light was determined by the ratio of two other measurable quantities, the electric permittivity and the magnetic permeability of free space. Maxwell's equation combined those two constants and produced the speed of light. This was the first demonstration that what had appeared to be independent constants were in fact related by a deeper theory. It was a hint that the list of 26 independent parameters might eventually shrink as our theories deepened. Einstein's special theory of relativity made the speed of light not just a measured constant, but a structural constant of spacetime itself, the maximum speed at which any causal influence can propagate. In doing so, it changed the meaning of c from a parameter of electromagnetism to a parameter of spacetime geometry, and his general theory of relativity made the gravitational constant g not just a measured number, but a coupling between the curvature of spacetime and the distribution of mass and energy. The deep theories do not just use the constants. They give them meaning. They embed them in a framework that tells you what they are constants of. The next step in this sequence of deepening understanding is presumably quantum gravity, the step in which G and H and C are not three independent constants, but aspects of a single, more fundamental framework. In string theory, as currently formulated, C and H bar appear naturally as properties of the string dynamics, while G emerges from the string coupling and the geometry of the compactified dimensions. The three constants that seem most independent from the perspective of the current non-unified theories may eventually be seen as different aspects of a single object in the final theory. How many truly independent constants there are at the deepest level is not known. It may be fewer than 26. It may even be zero in the sense that a mathematical structure that is unique and self-consistent might have no free parameters at all. There is a measurement being made continuously around the world that touches on this question in a way that is not always fully appreciated. Atomic clocks designed to keep time for telecommunications satellites and GPS navigation are also the most sensitive probes we have of whether the constants drift over time. A GPS satellite requires its clock to be accurate to better than a few nanoseconds. The position accuracy of GPS depends directly on the timing accuracy of the satellites. This means that essentially every smartphone user in the world is indirectly benefiting from the most precise measurements of atomic transition frequencies ever made. And those same measurements are simultaneously placing bounds on the variation of fundamental constants that no dedicated physics experiment has yet matched. The interplay between applied technology and fundamental physics runs through the entire history of the constants. The development of atomic timekeeping for navigation drove precision to the level where testing fundamental physics became possible as a byproduct. The development of optical frequency combs which allow extraordinarily precise comparisons between different atomic transition frequencies was originally driven by the need for better frequency standards in metrology. Its application to tests of the constancy of alpha and the proton-to-electron mass ratio was a secondary consequence. Technology and fundamental science have always fed each other in this way, and the constants of nature sit at the center of that exchange, because every precise measurement of any physical quantity ultimately bottoms out in the values of the fundamental constants. And so, we arrive back at where we started, the universe described by 26 numbers that we measure and write down and use and cannot currently explain: the electron mass, the muon mass, the 6 quark masses, the 3 lepton mixing angles, the 3 quark mixing angles, the phase in the quark mixing matrix, the 3 gauge coupling constants, the Higgs mass, the Higgs vacuum expectation value, the cosmological constant, the parameters of the neutrino sector, each of them an input, not an output, each of them a mystery wearing the disguise of a number. We are made of these numbers. Our existence depends on them. Our universe is shaped by them. And the question of why they are what they are is the deepest question that physics has yet found a way to ask without yet finding a way to answer. The fine structure constant, 1/137, sits on laboratory walls around the world. The greatest physicists of the 20th century stared at it and could not derive it. The greatest physicists of the 21st century are still staring. The universe has given us the number. It has not yet given us the reason. You have been watching the entire history of the universe. Do not forget to like and subscribe, and we will see you next time.